Have you ever wondered if the continents in the world right now were like puzzle pieces that perfectly fit each other? Well, you've come to the right place.
Hey, I'm Gio, the one and only time-traveling geologist. In order to answer your question, let's take an adventure through time along with my buddies, featuring the amazing history of the world and the unique story the continents wants to tell. Prepare your time machines, travelers, as we take you back in time to where everything started. Welcome to Geology.
Launching in 3, 2, 1.
We have arrived at the first destination. This young aspiring man working on his paper is Alfred Lothar Wegener, a German meteorologist and geophysicist born on the 1st of November 1880 in Berlin, Germany. He formulated the first ever complete statement of the continental drift hypothesis.
As a geophysicist, Alfred Wegener proposed that continents were once united into a single supercontinent called Pangaea, meaning all land on Earth was clumped up together surrounded by a massive ocean called Pantalasa. But it broke up long ago and the continents then moved to the positions you recognize today.
After further research, he discovered three pieces of evidence to support his hypothesis about continental drift. First, the fit of the continents. Wegener was very much fascinated and impressed with the similarities in the coastline of eastern South America and western Africa. Seemed to perfectly fit together rather like a jigsaw puzzle piece, and speculated that those lands had once been joined together. To prove Wegener's second evidence, let's go back to Mesozoic era. Get excited because you are about to experience a first-class view of dinosaurs.
Launching in 3, 2, 1.
Wegener found the fossils of several species like the Mesosaurus into peculiar places. The very southern tip of South America and the southern tip of Africa. In other words, opposite continents. Mesosaurus are freshwater reptiles. It couldn't have crossed the other side since it could not survive the salt water and compete against the apex predators of the ocean at that time like the 21-meter Ichthyosaur, Shonisaurus sikinensis, or the ever-terrifying Plesiosaurus.
The 1 meter long Mesosaurus would simply be food for these apex predators before it could traverse the Atlantic Ocean. But we deduce things not with how we think it should be, but how it actually is. Thus, he concluded that the continents were once closer to each other, making it possible for the Mesosaurus to travel from one coast to another. More examples of fossil record mishaps like this can be seen in the Cynognathus, Triassic land reptiles that are found in the South America and Africa, the Lystrosaurus in Africa, India, Antarctica, and Glossopteris, a fern that is found in all of the southern continents.
And lastly, the past climate data, where he discovered evidence of glacial stations on bedrock. These are linear scratches or grooves left behind by moving glaciers. He found this in the Amazon rainforest, on the equatorial South American continent, and hot the jungles of South Africa. So he assumed that the continents weren't always near the equator, but were at some point closer to the poles, enabling the formation of glaciers.
He later on took a closer look at bituminous coal found in Antarctica and found that they were indeed identical in composition to coal found in other continents. To spare you the details, essentially, bituminous coal production is only possible if a swampy biome exists in a bitter cold environment like the frigid Antarctica is not gonna allow such an environment to exist. But what if Antarctica was not always in the polar caps? Then it is possible.
Even with mountains of evidences to support his claim, Wegener's theory was completely denied and discarded by other scientists and scholars, because he could not answer one very important question. How? How can something as big as continents move? If his theory was correct, what is causing them to drift?
This brings us to the main topic of this video, plate tectonics. We've discussed how we figured out that the continents were moving. Now let's find out why they're moving, shall we?
Before that, let me tell you what plate tectonics is. To put it simply, the theory of plate tectonics states that the planet's crust is broken and segmented apart into what we call plates. There are two types of plates: continental plates, which are above sea level, and oceanic plates, which are below sea level. The interactions between these plates are what causes land formations and earthquakes. Okay, now that you are caught up to speed, let's continue.
As some of you may know, our planet is segmented by three major layers: the crust, the solid surface of the planet where you and I live; the mantle, the large, dense, and thick layer of molten rock found below the crust; and the core, a ball of pure iron at the center of the Earth that is as hot as the sun's surface. This massive heat energy emanating from the core is the key to understanding the moving force of the continents.
The core heats up the liquid mantle, which causes it to become less dense and rise up to the top. It then cools down and sinks to the bottom, starting the cycle over again. This cycle is what you call convection current, the driving force of plate tectonic. You see, when the heated mantle rises to the top and hits the bottom of the crust, it is forced to move sideways before sinking, bringing the plate along with it.
With that said, I know what you're asking. What happens when two plates interact? A lot happens, and it depends on the direction in which the plates go. When two plates move towards each other, this is what you call a convergent plate boundary. In a continental to continental convergent plate boundary, mountains usually form. But what's more interesting and important are continental to oceanic convergent plate boundaries. Here, instead of a mountain ranges, a subduction zone forms instead, where the denser oceanic plate folds down towards the mantle. We'll come back to this later. Another one is a divergent plate boundary. Here, the plates move away from each other. In a continental to continental divergent plate boundary, rift valleys form, and in an oceanic to oceanic divergent boundary, a mid-ocean ridge forms instead, where the crust becomes pulled apart by the two diverging plates, exposing the mantle below, which spews out and cools down and becomes a part of the seafloor. This process is called seafloor spreading. Now, you might be thinking, where does the seafloor spread to? It can't keep spreading indefinitely, right? Let's go back to subduction zones. As previously stated, in a subduction zone, the denser oceanic plate bends towards the mantle, where it melts and gets recycled. See? Isn't that neat? Eventually, everything goes back to where it all began.
I have told you the intriguing story of Mr. Reginer and his theory of continental drift, about plate tectonics and the many interactions between tectonic plates. We're back home, so it seems this is where we part ways. Don't worry now, we'll see each other again on the next installment of Dio the G.